Hello, I wanted to take a few moments and walk you through the keys to the practice exams. So this is the exam practice for chapters 11 and 12 material. So the first problem here, we have the mass of a small block of metal reads 0.35 kilograms when weighed in air, and then when we completely submerge it in water, the same spring scale reads 0.27 kilograms. What is the density of this metal? So we have the mass in air and we have the mass in water, which gives us both the true weight as well as the apparent weight. So when I do 0.35 kilograms minus 0.27 kilograms times g, what I'm getting is the buoyant force, the difference between the true weight and the apparent weight. And I just did it kind of lazy here, so I did kilograms times g. So the difference is 0.08 kilograms times 9.8 gives us 0.784 newtons is the buoyant force. That's what we get when we do it that way, based on the apparent weight and the true weight. If we do it based on the definition of buoyant force equals density of the fluid times the volume of the object times g, we figure out that the volume of this object is going to be 0.784 newtons divided by the density of water, 1,000 kilograms per meters cubed, times 9.8 meters per second squared. That gives us a volume of 8 times 10 to the negative fifth cubic meters. All right, now we have the pieces to put together. The density of the object is the mass of the object divided by the volume of the object. So the mass of this small block of metal is 0.35 kilograms when weighed in air. That's the true mass, divided by the volume that we figured out by this difficult thing, gets 4,375 kilograms per cubic meter as the density of this block of metal. All right. So if you're going to water your yard and you use a hose of diameter 3 centimeters, water flows from the hose with a speed of 1.5 meters per second. If you partially block the hose to an effective diameter of 0.5 centimeters, what is the speed that the water flows with? So area equals pi r squared. So we were given the diameter in centimeters. I'm going to convert to meters because I'm going to do things in meters per second, right? So I have to have all the units agree. I don't really, because they cancel out with each other, but I'm a little bit weird that way. So area 1 is pi times the diameter divided by 2, 3 times 10 to the negative second meters. That's what 3 centimeters is. Divided by 2, take that, square it, times pi. I get 7.07 times 10 to the negative fourth square meters. Same deal with the other area. And then since A1 V1 equals A2 V2, I'm looking for V2, this the new speed, the new velocity. V2 equals A1 divided by A2, A1 divided by A2, times the original velocity, 1.5 meters per second. And I get a new velocity of 54 meters per second. So I really, blocked that hose really small and had a huge increase in velocity. All right, density. Density equals mass over volume. So we're given the density, we're given the mass, we're going to solve. Nope. We're given the density, we're given the volume, we're going to solve for the mass. So density equals mass over volume. Mass equals density times volume. Density times volume, didn't even need to convert anything, 56 kilograms. Nice and easy. All right, the ice on a lake is 0.101 meters thick. The lake is circular with a radius of 280 meters. Find the mass of the ice. So we're able to find the volume of the ice. Volume equals pi r squared h. So pi times the radius squared times the height gives us a volume of 2,463 cubic meters. since the density of ice is 917 kilograms per cubic meter times 2,463 cubic meters, we get a mass of 2,258,578 kilograms, or 2.25 times 10 to the 6 kilograms. All right, a beaker is filled to the brim with water. A solid object of mass 3 kilograms is lowered into the beaker so that it's fully submerged, and 2 kilograms of water flows out over the rim. What is the buoyant force that acts on the submerged object? And when you release it, does it rise, sink, or remain in place? So the buoyant force equals the weight of the displaced fluid. I was told the mass of the displaced fluid is 2 kilograms times 9.8 meters per second squared, gives me a buoyant force of 19.6 newtons. All right, I was also told that it had a mass of 3 kilograms, so the true weight is 29.4 newtons. So the net force on the object is the downward force of 29.4 and the upward force of 19.6. I get a net downward force, so it will sink down. Our poor polar bear is out there on his little iceberg. So I have the density of ice and the density of seawater and the polar bear sitting on it. What is the weight of the heaviest bear that this ice can support without sinking completely beneath the water? So if our ice displaced its entire volume in water, then it would be a buoyant force of, I figure out given the volume of the iceberg, times the density of seawater times G. I get 47,211.5 newtons. But the ice itself only weighs the volume of the ice times the density of ice times G, 42,237 newtons. So the heaviest polar bear could be the difference between the two. So 4,974 newtons. I guess I did say weight. I could also figure out that the mass would be 507 kilograms. Hey, what's going on here? We have two liquids. They're in equilibrium. I see liquid 1, I see liquid 2. Above the line, there is less liquid 2 than there is liquid 1, but it must be the same mass of liquid above the line in both cases. So if liquid 1 has a large volume for a small mass, or a small mass for a large volume, then it must have less density. It must be less dense than liquid 2. Waterbed, there are the dimensions. We are worried about exceeding 6,660 newtons. So should we purchase the bed or not? So what we do is we figure out the mass of the bed, density times volume, then the weight of the bed, and we figure out that the bed doesn't exceed the maximum. Sorry, I'm texting my wife as I record this video. All right. Beaker filled to the brim with water. This sounds familiar. 2 kilograms located in during the process. 1.5 kilograms of water flows out of the rim. Buoyant force. So it was a very similar question. It still sinks. It's still a net downward force. I shouldn't ask that question twice on the real exam. Blood is flowing through an artery. We have the radius. We have the rate. Now we're asked to determine the flow rate and volume that passes through the artery in a period of 30 seconds. So Q, this isn't heat from thermodynamics, this is Q from flow rate, is area times velocity. So we figure out the area. We're going to do this in centimeters because we have a velocity in centimeters per second. So we figure out the area pi r squared, radius 2 millimeters. So there's 100 millimeters in 1 centimeter. So we convert this to centimeters and then figure out the area. So we have the area in square centimeters. So Q equals AV, so the area times the velocity. We get part A, determine the flow rate, 5.02 times 10 to the negative second centimeters cubed per second. And then in 30 seconds, that would be 1.51 cubic centimeters of blood through that artery. All right, we have another hose. We have an internal diameter, 1.6 centimeters. What is the flow rate in liters per second? And the fluid velocity in the hose's nozzle is 1.5 meters per second. What is the nozzle's inner diameter? So, what do we do here? So we have the flow rate. We're doing that again. And we figure out what's going on there. Why did I do liters per second? I guess I just decided to. So A1 V1 equals A2 V2. So A2 equals A1 V1 divided by V2. So we figure out the new thing. So part A, what is, oh, that's why, because it asked what it was in liters per second. So what is the flow rate in liters per second? We convert cubic meters per second. There's 1,000 liters in a cubic meter. Figure that out. And then for the second part, we go ahead and figure out the new area. And then convert to diameter by the process just the opposite of figuring out the area based on the radius. So area equals pi r squared. So then radius equals the square root of a over pi. And so we figure out the diameter. All right, water flow from a spigot at the bottom of this 1.25 meter tall container. So we take our Bernoulli's equation, but the pressure is the same at the input and output. The density of the fluid is the same. V2, the velocity up here, is so small compared to V1 that we pretend it doesn't exist at all. And we simplify the equation to 1/2 V1 squared equals GY2. So V1 equals the square root of 2GY. V1 equals 2GY equals 4.95 meters per second. The water flowing out at the bottom of the spigot is coming out at the same rate as if I took a rock and dropped it from this height and let it fall. It's a conservation of energy question. All right, that was practice exam 1. I wanted to get to practice exam 2. Oh, it's making me mad. So there's 2 parts to the practice exam for this exam number 1. So the first one was chapters 11 and 12. The second part is chapters 13 through 15. So we have our cabin. It has a wooden floor. What we're going to be talking about is heat transfer by conduction. This was chapter 13 material. That was a video. So Q equals Ka delta T times T divided by the length, the thickness. So Q over T on both sides of the equation, Q divided by T, I'm going to divide both sides of the equation by T, time. I get the rate, Q over T equals Ka delta T, capital T for temperature, divided by the thickness. So I have K, the thermal conductivity constant for this wooden floor. I have the area. We were given that. We have the change in temperature, the difference in temperature between the inside and the outside, divided by the thickness of the floor, gives us 408.8 watts. That's the rate of heat flowing out through that floor. On a cold winter day in your wooden cabin, you can feel the heat flowing out. All right, the interior of a thermos bottle is silvered to minimize heat transfer by radiation. So the silvered walls are mirrored walls. They reflect the radiation back into the liquid. So if you're going to lose heat by radiation, you would lose it by it being absorbed into some other material, like your black car parked in the sunny parking lot is absorbing solar radiation and it heats up. Whereas if you had a mirrored surface, it reflects the radiation heat back off again. So that's what goes on with a thermos bottle. Hey, the temperature of a monatomic ideal gas with a mass per mole of 0.00750 kilograms per mole is measured at 298 K. The absolute pressure is 1.65 times 10 to the 5th pascals when its volume is 1.21 times 10 to the negative 3rd cubic meters. What is the mass of the gas? All right, so PV equals nRT. So N, the number of moles, is PV over RT. PV, given that, over R. The physics R is 8.31 joules per mole Kelvin times 298 K. So we have 0.0806 moles. So each mole has a mass of 0.0075 kilograms. So multiply those numbers together and we get 6.05 times 10 to the negative 4th kilograms. Complete the following statement. The absolute temperature of an ideal gas is directly proportional to the number of molecules. No, doesn't matter. Average momentum of the molecules. No, that's not it either. The average translational kinetic energy, Ke equals 3 halves kT. That sounds right. The amount of heat required to raise. No, now we're talking about the specific heat. The relative increase of the volume of the gas for the temperature increase. No, that's just crazy talk. So the average translational kinetic energy of a gas, Ke equals 3 halves kT. That means that that's proportional to the absolute temperature. Hey, an ideal gas absorbs 750 joules of heat as it performs 625 joules of work. What is the resulting change in temperature if there's 1.3 moles of gas in the system? So the first law of thermodynamics, the change in internal energy equals Q minus W. So Q, we're giving it absorbs heat, so positive 750 joules. It does work, so positive 625 joules of work. So the change in internal energy is 750 joules minus positive 625 joules. That means that the change in internal energy, it's a modest increase in internal energy because it absorbed a lot of heat, but it also lost energy by doing positive work. So we wind up with a change in internal energy of 125 joules. Internal energy equals 3 halves nRT. So delta U equals 3 halves nR delta T. So delta T equals delta U divided by 3 halves nR. We have delta U 125 joules divided by 3 halves N, the number of moles, R, the physics gas constant, and we get an increase in temperature of positive 7.7 Kelvin. Hey, if you put a room temperature helium-filled balloon in a cold refrigerator, will its volume increase, decrease, or stay the same? Well, let me tell you that if we do that, if it starts off with a high temperature and it goes to a cold temperature as it reaches thermal equilibrium, then volume equals nRT divided by P. If we assume that N, R, and P are constant, then if the temperature goes down, so does the volume. So it would decrease. All right, so temperature of a substance is held fixed. So we look to our equations for the one that is set for isothermal. So the isothermal portion of a heat engine is where work equals Q and delta U equals 0. So if the temperature is held fixed, is it possible for heat to flow into or out of the system? In each case, give an explanation. Well, we can add heat to the system and have that heat do work, and there would be no temperature change. Or we could have the heat do work on the system. So if you have ice and you add heat and the temperature doesn't change, then we can heat up or not heat it, convert the ice into liquid water. Also, you can do it the other way, part B. If you have heat's flowing out of the system, then you can do that. All right, so we have a thermodynamic process. So number 8 and number 9 are related to each other, and number 9 has some values filled in. So here, for each part of the cycle, we're going to state whether the work done by the system is positive, negative, or zero. So A to B, the volume doesn't change, so the work is 0. B to C, the volume decreases. If the volume decreases, then we're going to have negative work. And C to A, the volume's increasing. So if we have an increase, then we have positive work. Now to fill in the nitty-gritty, A to B, the heat flow, it lost 53 joules. So here, for that one, we're going to say, all right, so delta U equals Q minus W. So delta U equals Q minus W. 0, we said that because the volume doesn't change, so delta U must equal negative 53 joules. So we filled this one in. This is like a Sudoku puzzle if you're one of those people. All right, B to C, we're given Q, we're given W. All we need to do is figure out delta U. So delta U equals Q minus W. So negative 280 joules minus negative 130 joules gives us negative 150 joules. C to A, it's going to return to its original state. If it goes back to its original state, then all of the heats, all the changes in internal energy, if we had a decrease here for part B and another decrease for part C, we have to add all of that heat back in to get back to its original state. So in order to add that heat back in, we just take negative plus negative and then find out what we need to add to it to make it be 0. So it'd be 203 joules. And then we do our delta U equals Q minus W, but now we want to solve for Q. So Q equals delta U plus W. So delta U, we figured out, positive 203 joules. W, positive 150 joules. That means that the heat that we added in order to get this piston back to its original state was 353 joules. It was doing work and it was heating up the system to return it to its original position. Hey, when 1010 joules of heat are added to 1 mole of an ideal monatomic gas, its temperature increases from 272 to 276 Kelvin. Find the work done by the gas during this process. So delta U equals 3/2 nR delta T. So N, 3/2 is 3/2. N, 1 mole, R delta T, 4 Kelvin, equals 49.9 joules. Q was positive 1010 joules. We're told that. So work equals Q minus delta U. So Q minus delta U, 960 joules. A heat engine takes 1,420 joules of heat from the high temperature reservoir and exhausts 660 joules into the cold temperature reservoir. How much work is done in this system? So work equals QH minus QC gives us 760 joules of work was done. And that takes us to the end of that. So hopefully you're feeling in pretty good shape. And see you.